is to look for some factoring or some long division that could be done. When we start to work an integration problem, we realize that we aren't going to be able to find a u and then find the du that's going to appear in there because I need to multiply variables in, and we don't have a rule that allows us to do that. We can multiply in constants, 2, 7, but I can't multiply in an x and divide an x out. So as I look at this first one, I see in the denominator I've got this beautiful polynomial, but I've got no factors of x to be its derivative. So if I let u be x squared plus 8x plus 16, I need a 2x plus 8 to be my du dx, and therefore I'm not going to be able to find that. So one suggestion when you come across ones and you can't pick out an easy embedded u is to at least consider, could I factor or do some division? In this first case, I would try to factor this, and it turns out that when you factor this, it will be equivalent to, that's a perfect square trinomial, and when it factors, it's going to factor and look like that. And the benefit of doing that then is now I have an embedded function. I could let my u substitution be x plus 4, whose derivative with respect to x would be 1, so my du dx would be 1, or my du and dx are the same. The derivative of u is 1, the same as the derivative of x. So when I go to set up my substitution over here, I'm ready to go right to u's. And I could make this 1 over the quantity u squared du. Therefore, when I go to actually do my integration, and some of you might prefer to think of this one then as u to the negative 2 du, when I go to get my integral, I'm going to have negative u to the negative first plus a constant. And when I go to write this out as my final answer after my u substitution, I could have, then I'm going to put my factor of u in the denominator plus constant. So in that case, factoring helped us find something that we could use a u substitution for and have its derivative. In the next one, remember to slow down the video, pause it, catch up, try this out. In the next one, if I made u the numerator, I'm going to have trouble having du in the denominator because I don't need it in the denominator, I need it out as a multiplier. So one thing you can do if the power in the numerator is higher or equal to what's in the denominator is I could do some long division and come up with a different expression worth the same that this is equivalent to and see if taking that one's integral will be any better. So as I divide by, and this is going to take you back a little, as I divide by that, okay, and you can do all your work through, okay, you come up with x plus 4, and then there's this extra 6 left over. And you can carry out the long division to find that. So they're telling me that that expression is equivalent. So in other words, if I did the integral instead of the quantity x plus 4, plus, and I'm going to pull the 6 and that apart a little bit to help my brain see possibilities for integration. I don't think I'll even need to use substitute here now that I've rewritten this into 3 separate terms. I can integrate each one. So the integral of x then will be 1/2 x squared, integral of 4, plus 6 times the integral of 1 over x minus 1 will be 6 times the natural log of x minus 1 plus a constant. I cannot remove the absolute values off of this instance of natural log because x minus 1 might be a negative number or 0 and therefore would not work in the natural log. So I need to keep those on there.